Hi everyone! In this video we're going to learn about contingency tables and association. What we're going to be doing here is we're going to be dealing with two qualitative variables instead of two quantitative variables like we've seen in the past. Okay, so we're going to jump right into it with this example. So consider the data, and this is measured in thousands in this table, and it represents the employment status and level of education of all U.S. residents 25 years or older as of November 2018. So notice our table has rows, and the rows correspond to the employment status, and then it has columns, which correspond to the level of education. So this table is referred to a contingency table or a two-way table because it relates two categories of data. In this case, the row variable is employment status, and then the column variable is level of education. And then each box inside the table where there's values, that's considered a cell where the rows and columns meet. First thing we're going to do is compute the marginal distribution of a variable. So a marginal distribution of a variable is just the frequency or relative frequency distribution of either the row or column variable in the contingency table. So it's basically going to come from the totals of either the rows or columns. So find the frequency marginal distributions for employment status and level of education from our table. Okay, so here was our table. And so what we're going to do is we're going to take some totals. So the blue entries over here in this column, they represent the marginal distribution of the row variable employment status. So it's just the totals from the employment statuses, either employed, unemployed, or not in the labor force. And then the red entries represent the marginal distribution of the column variable level of education. So we have did not finish high school totals, high school graduate totals, and so on. And so the marginal distribution for employment status actually removes the effect of level of education. And then very similarly, the marginal distribution for level of education removes the effect of employment status. So the marginal distribution removes the effect of the other variable. So the marginal distribution of level of education shows that there were actually more Americans with a bachelor's degree or higher than there were Americans who were high school graduates. So the numbers were 79,248 times 1,000, so that's in the millions, and then versus this other value, and this was in that year and month. And so the marginal distribution of employment status shows that 137,704 times 1,000 Americans were employed. And then the table also indicates that there were 220,813 times 1,000 U.S. residents 25 years or older. And so the marginal distribution gives us some nice totals. So we want to determine the relative frequency marginal distribution for both level of education and employment status. So we already have our totals in our rows and columns, and we're trying to find the relative frequency. So based on some calculations, and we've talked about relative frequency in the past, we take our value that we're working with, in this case it was our total of, let's go with row 1, employed, over the total number. Okay, so the total number, if you recall, a couple of slides back, it was the total of the marginal distribution of level of education. Well, level of education was down here, and then it was where it met with the totals of employment status. So that 220,813 number was in the bottom right corner. So that's actually our denominator. So we have our marginal relative frequency marginal distributions here for our employment status, and then down here for our levels of education. And so what we can see is that 9.9% of U.S. residents 25 years or older did not graduate from high school. That's this one right here. You can also see that 62.4% of residents 25 years and older were employed at this time, and that's this number right here. So we can see a few different things. All right, next we're going to use the conditional distribution to identify association among categorical data. So what proportion of the following groups of individuals is employed? A, those who did not finish high school. B, high school graduates. C, those who finished some college. And D, those who have at least a bachelor's degree. Okay, so in November 2018, 21,839,000, so that's actually 21 million, individuals 25 years or older did not finish high school. And that's from our totals right here. And so of this number, 9,607,000 were employed. So what we're going to do is we're going to take that proportion. So we're going to just divide the employed amount that didn't finish high school by the total that didn't finish high school. So we get our proportion of 0.440, or you could say it's like 44%. So this represents the proportion of individuals who did not finish high school who are employed. You can do very similar calculations for the other three columns. So 34,625 over the total of 62,325 gives us a value of 0.556 or 55.6%. And this represents the proportion of individuals who graduated from high school and are employed. And we can do the same thing for the some college category, and we'll get 0.634. And then last, similar calculation, the amount employed over the total from the column of bachelor's degree or higher, and we get a proportion that's 0.721 or 72.1%. So what we can see from these relative frequencies is that as the level of education increases, the proportion of individuals employed increases. Now, a conditional distribution lists the relative frequency of each category of the response variable given a specific value of the explanatory variable in the contingency table. Now, in our example, if we're trying to find out the employment status by level of education, then that would mean that the level of education would be our explanatory variable, and the response variable would be employment status. So find the conditional distribution of the response variable employment status by level of education, the explanatory variable from our table. What is the association between level of education and employment status? So we're going to use the number of individuals who did not finish high school as the denominator and computing the relative frequencies for each employment status. Okay, so we have, notice the same denominator in the three employment status categories, and are changing numerators based on were they employed, unemployed, or not in the labor force. But this is all for did not finish high school. Then use the number of individuals who graduated from high school as the denominator and computing relative frequencies of each employment status. So similar calculation, but this time our denominator is from the total of people that that had a high school diploma. And similarly for some college and bachelor's degree or higher. And then notice that the totals are all 1 here, because remember our relative frequency is always going to be 1 or 100%. So we're going to read this information on our table from left to right. So as the amount of schooling, the explanatory variable, increases, which is left to right, then the proportion employed within each category also increases. As the amount of schooling increases, the proportion not in the labor force decreases, and the proportion unemployed with at least a bachelor's degree is much lower than those unemployed in the other 3 levels of education. Okay, so just notice as we move right and the level of education goes up, so does our relative frequencies. Okay, and then, but for unemployed, it goes down. as your education level goes up. And then for not in the labor force, it's also going down for the higher education level. Now, information about individuals' levels of education provides insight into their employment status. So that's something we can conclude. The association between level of education and employment status allows us to adjust our predictions. So using the results of the previous example, we're going to draw a bar graph that represents the conditional distribution of employment status by level of education. Okay, so here's our bar graph. We have on our horizontal axis our level of education. We have on our vertical axis the relative frequency. And then for each category, we have 3 colors and 3 bars because we have our 3 employment statuses. So as we can see from the height of each bar, blue being employed, so this is a visual for what we just talked about, the level of education increases, the height of the blue bar increases, which means that the employment status is higher, the higher the education. And then similarly, but the opposite for not in the labor force, notice the green, the height of the bar is decreasing as the education level increases. And it's a little bit hard to tell with unemployed because it's such a small bar compared to the rest, but notice it is actually getting shorter as we get over here. So what we can do instead of drawing a conditional bar graph, we can draw a stacked or segmented bar graphs. And in these graphs, there's actually 1 bar for each value of the explanatory variable. So for us, that's for each level of education category. And then each bar is then divided into the segments for our response variable. And so the height of each segment within a bar represents the proportion of observations corresponding to that variable. So notice that the total height of each of the bars is 1 because the relative frequency total is always 1. And then we have to just do a little bit of using our number line here to figure out the actual relative frequency values. For example, let's pick this one. It's close to a line. For high school education, we have our unemployed. It looks like at almost 0.6, we'll say 0.5 something. And then the not in the labor force makes up about the other 0.4 something. And then we have just a little bit for unemployed, which we'd have to go back to our table to get an exact value, but maybe 0.1 something. Now let's talk about Simpson's paradox. So let's take a look at this example. The data in this table show the admission status and gender of students who applied to the University of California at Berkeley. From our table, we can see that the proportion of accepted applications is about 39.5%, and we get that from the total for accepted over the whole total, which is that applied. And then the proportion of accepted men was about 46%, and the proportion of accepted women was about 30%. And so we just get those by taking the value, for example, for women of accepted over the total number of women that applied. So on the basis of these proportions, a gender bias suit was brought against the university. The university was shocked and claimed that program of study is a lurking variable that created the apparent association between admission status and gender. So remember we talked about lurking variable. It's that variable that's not accounted for in the study, but that could affect the results. So the university supplied the following table in its defense. So we're going to develop a conditional distribution by program of study to defend the university's admission policies. So let's just talk about this table real quick. So accepted is A, not accepted is NA, and then there was 6 programs of study, and we don't necessarily know what they are, but they're represented by A, B, C, D, E, and F, and then they are still broken down by gender. So the proportion of men who applied to program A were accepted was about 61.9%, because it was the total accepted over the total that applied which came from accepted and not accepted. The proportion of women who applied to the program and were accepted was about 82%. And so we have the conditional distribution for the other remaining programs. So similar calculations will get these conditional distribution values. So notice what we have, the two that we just talked about for men and women of program A. For program B, it looks like the amount of women accepted was higher as well, 68% compared to 63%. Program C, they're roughly about the same. Same for program D. Program E seems like just slightly more men, and then program F, more women. So the figure shows the bar graph of the conditional distribution in the table we just looked at. The blue bars represent the proportion of men admitted for each program, and the green bars represent the proportion of women admitted for each program. Okay, so how does this look? It looks like for women, the relative frequency for accepted is actually higher most of the time. So 4 of the 6 programs actually had a higher proportion of women accepted. And the proportion of men accepted in programs C and E is really not that much higher than the proportion of women. So the initial analysis didn't account for the lurking variable, which was program of study. There were many more male applicants in program A and program B than female applicants, and these two programs happen to have higher acceptance rates. So the higher acceptance rates in these programs led to the false conclusion that the University of California at Berkeley was biased against gender admissions. So from our example, the association between gender and admission reverses when the lurking variable program of study is accounted for in the analysis. And so this illustrates a phenomenon known as Simpson's Paradox. So what Simpson's Paradox says is that it describes a situation in which an association between two variables inverts or goes away when a third variable is introduced to the analysis, was what happened with introducing program of study into the analysis. All right, that's it for this one. Thanks for watching.